How's everyone? Doing good? Wednesday. Yeah, so it's the day of review today. You have tomorrow, and then Wednesday afternoon we have the exam. So I'm going to highlight a few things. I believe I've got videos for all of the solutions. So we have this module in Canvas for test 3, has all of the resource content. You can look through this learning resources, so there's some additional videos in there. But today we're going to go through these in-class reviews a bit. There's one that has some highlighted questions, and again I did that to kind of shorten down the review a little bit to make it maybe closer to what the test will be like. Test is 8 multiple choice questions with 4 open answer questions. So total of 12 numbered questions. Some of the ones open answer have multiple choices or multiple parts. So that's in there. There's this test 3 review, and it's got various exam reviews from various semesters, but what it does have is you'll see that those reviews are pretty much the same, not almost identical. Then I went and worked through a few of the review solutions, and I think you'll see each of those come from what we're going to take a look at. So each of the questions are worked through. So if you have questions, take a look at those. It'll take you all the way through. So we've got 13.1, 13.2, 13.3, 13.4, and then 14.2. So just 5 sections for this test, just focusing on the integration. So those are all there, and something good to review through. Even if you've worked through them or something, maybe just watch them and let it sink in, get some popcorn out, whatever you want to do. But I think that's good. This is where you would upload a snapshot of your working through the review for the quiz points. And again, the more you work through, the better. The other thing I wanted to highlight, when did we do that? Area between 2 curves. I highly recommend, I'll go to the slide desk, reviewing this part. It's on the video, but let's see. This question we worked through together. There's ones like it, but just especially the steps, be able to do each of those parts. Watch the way I did it, and you'll be in good shape. Okay, so be able to do all the things we did when we talked about this one. And then let's see. So this is, let's make it a little larger. So what are the things you need to be able to do? You need to be able to get the antiderivative. And again, remember, we went through several parts. We went through this indefinite integral, and then we went to the definite integral, and both have sort of that same part of you need to get the indefinite integral. And do it this way. So just sort of some notes. When we are integrating anything to a power, any kind of power, could be a negative power, could be a fractional exponent, could be any exponent, right? To get its antiderivative, we take that exponent, we add 1 to it, and then we divide by that new exponent. And we either plus a constant for the indefinite, or when we got to the place where we were talking about definite integrals, let's just take an example, x to the 5th. How about, or yeah. Or how about x to the 0.5, which is also the square root of x, right? The half power. To integrate this, we're going to get x to the 1.5, adding 1 plus 1 point plus 0.5. We're going to divide by 1.5, and then we're going to evaluate this from a to b, whatever those numbers are, right? And so we end up with b to the 1.5 divided by 1.5 minus a to the 1.5 divided by 1.5. So that's the definite integral. That's the indefinite integral. So we did both. So we started off with the indefinite integral, and then by, I think it was, 13.4, we got to the definite integral. And we really were doing the same thing, except we, instead of having to go plus a c, we looked at the boundary points and plugged those in. So that kind of takes you from the beginning to the end of what we did. And then remember, when we had two curves finding the area, this really gives us the area between the curve itself and the x-axis, which is y equals 0. And so 14.2 is just a special case that the second curve was not y equals 0. So we'll take a look at that. But if we could do this, this is most of what we were doing. There was a few special, so those if we have an x to a power, right? And if you have a polynomial, so you have more than one term, you just integrated term by term. So it was just like, you got 5 terms, it's like 5 different problems. I'll look at a special case. What if we had integrating a number? Again, this is sometimes more difficult because there's no x to add a 1 to, but remember this is just going to be 5x. Again, either plus a constant, or if it's a definite integral, evaluating it from a to b. Okay, so a number, when it integrates, it becomes 5x. All right. There's 2 other special cases, exponentials. If we have e to the x, that is its own antiderivative. And the other special one was the integrating 1 over x, or it could be written as x to the minus 1, right? These integrate both the same. That integrates as the natural log of x. So those are 2 you just need to sort of memorize. And e to the x is simple, but it's also complicated because it doesn't feel like we're doing anything. So it's also one that's easy to miss. Nah. That's more just to deal with the, yeah. See, I don't do it, so why should I mark you off for something I don't do all the time? So, yeah, usually the answers, WebAssign probably wants you to put this because that makes the domain correct. But again, if you get 1 over x integrates to natural log of x, I'm very happy. So those were our special cases. Any questions so far? Okay, so notice we didn't have to deal with limits or anything. We just got right into sort of shortcut rules backwards. We had this use substitution. We'll do a few of those just to kind of get through for when we were integrating something that was the result of a chain rule. That was, which was that? That was 13.3? 13.2 was Riemann sums, so we'll do a few of those, and then we pretty much got it. But if you can, these are the basic things. We have to know these pretty good. Okay, so let's myself a blank page. All right. Any of these that you would like to take a look at? Maybe we could focus on the highlighted ones, but if you have one that's not highlighted, it'd be just as fine. So out of the 13.1, maybe we'll, if you see one later on, we'll come back to it, because I think it might be better to spend some time on the substitution. It's a little bit more complicated, because we'll see both of these. Which one shall we do? Which one would you like to see? F? All right. $15x. Oops. Okay. There we go. So we're integrating 15x square root negative x squared plus 7 dx. So on these with substitution, notice these are being multiplied, not added. So, I mean, maybe that kind of indicates there is also something that suggests an inside. And one of the things you see is you've got an x squared, and you know that the derivative of x squared is 2x, so that's probably where this outside stuff is coming from, remembering the chain rule. So this is why you'll see, when you see something like this, look for those sort of telltale signs. Even if they don't say use substitution, which they probably will, it indicates that. So we want to make the u part the inside, and so that's what we're looking for. And again, we'll look at a couple other ones, but inside is a grouping of something, and so whenever you got a radical, the inside of the radical is your natural choice. So negative x squared plus 7, and then so once we choose something for u, that's the big decision. Once we make it, then we set it, and then we take the derivative of both sides using what did we call that? Implicit derivatives. So the derivative of u is 1 du, so I just put du. Negative x squared, its derivative is negative 2. The 2 comes down. X to the first power. Derivative of 7 is 0. And then I remember to put that this was the derivative with respect to x, so dx. So I took the derivative of both sides, du on one side, dx on the other. Okay. Next step is to solve for dx. So I want to get dx by itself, because that's what's going to get replaced here. The u is going to go in there, so divide both sides by negative 2x. That cancels with that, leaving 1, so dx is equal to du over negative 2x. Okay. So now the next step is the substitution part. We're going to change this, and what's supposed to happen if we did everything, if we made the right choice, it's supposed to come to be something very simple, like maybe just the square root of u, or e to the u, or something very, very simple. 15x, we don't know what to do with it, so we'll leave it there. We've got the square root, and this stuff inside is actually, we renamed it to be u. dx is du over, and everything's a fraction, so I'm going to say this was all in the numerator. The negative 2x is in the denominator. Okay. And now it's not simple yet, but we see, oh, we got some algebra we can do. X divided by x is 1. And then I have 15 over negative 2. That's just a number, and it's being multiplied. So I can just say, okay, let's take it outside. Don't worry about it for now, and just multiply it at the end. And then we have, lo and behold, the very simple square root of u du. Or we could u to the 1/2, right? or u to the 0.5. And again, I don't care whether you use fractions or decimals when you're doing it with the open answer. You just have to, and if it's multiple choice, you just have to be able to recognize the correct multiple choice answer. So, and that's, so if you want to use decimals, I actually prefer decimals personally over fractions, but either way. So we integrate this now. It's going to be negative 15 over 2 u to the 1.5, and I'll just sort of continue the fraction part here, over 1.5. These are multiplied, plus a constant, and then we just sort of simplify. 2 times 1.5 is 3. Simple as that. So 15 divided by 3 is 5. So this simplifies just into 5. U to the 1.5, but instead of putting u, we're going to back substitute with what u really is. Remember, u is something we made up. Minus x squared plus 7 to the 1.5. So kind of, get the rhythm. Sometimes we do math, listen to some music that gets you, but it's find u, take its derivative, substitute everything in, do a little algebra to simplify it. It's got to become a very simple integration. This step always has to be easy. If it's not, we messed up with the substitution part. And there's a lot of ways to do that, but most of it is not going to be any more difficult than this. Again, the engineering calculus, they give them a bunch of really funky stuff to have to work with, and but we try to make it straightforward. Again, it's just a simple, u to the 1/2, add 1, divide by that, simplify a little bit, and then back substitute with what we started with. We could always check, remember, if we take this derivative, what should we end up with? What we started with. Okay, so but I would, if I'm taking a test, I would get the answer first, get everything else answered. I'd come back to this and then do a check. That's just me. But again, kind of find your way of doing it. The other thing, I think I am recording. I hope I'm recording. The other thing I want to encourage you to do, it's okay to work through these with notes. It's okay to view the videos and see through it, but also take some time to practice it without notes, okay? Like it was a test. Yes. What's that? Because it's a square root. So the square root is a 0.5 power, or a 1/2. Let's see, so this is 15. I took 2 times 1.5, which is 3. Probably should have wrote it out. So 15 divided by 3 is 5. So there was this, let me go ahead and write that. So on my scratch paper, so we've got 15, 2 times 1.5 is 3. So this reduced down to just 5 over 1, or just 5. Okay. And it's okay to, again, when you show your work, to do some things in your head. You don't have to show all the arithmetic and stuff, but again, the more you put down, the easier it is for us to see or have a conversation about. And I do have the final exam sort of review, so once we get, I just want you to know, once we're done with the test, so that's going to take up this week. If you want to start looking ahead, I did do I did a printed solution. I posted my solutions for exam 1 and 2. Those are from spring semester. I'll do ones for the ones we did this semester as well, so that, again, you could review yours. Again, as soon as we get done with this, it's good to start reviewing for the final. We do have a couple more sections, 2 or 3. I'm not sure how much we're going to have on the final, but there's 3 more new sections to do. But at the same time, if you go back and review, a large bulk of the final exam will be the older stuff.
Is it a negative?
Where's the oh, thank you. There's this, yeah, yeah. See, that's another thing. Know your shortcomings, and I know I'm going to do that. So, yeah, there's this negative right here. There's a negative right here. So there better be a negative here. Again, it would be a minor if I saw that. Oh, you had it here, but you forgot it. Sometimes I ignore it, or a very minor thing. But it is important, right? Because -3 and +3 are on the opposite side of the thing, so it can make a big deal. Thank you. Questions? All right. Anyone want to take a look at H? It's one of the hardest part of H is what do we make, what should we make the U, right? Let's go here. So we'll do the integral. Come on. The integral of 3 natural log of x. Come on. Over x. Any suggestions? What should we make U? First step, right? Natural log? Good call. Good call. I was going through it mentally. I was going to make x, but if you make x your u equals x, then du equals t. It doesn't help much. So I was kind of like playing chess. You think ahead. That wasn't going to help. You could make 1 over x, but if you take the derivative of 1 over x, you get x squared. That didn't help. But again, remember, we're thinking whatever we make u, we should get sort of a derivative that goes away. So if we make u equal to the natural log of x, then when we take the derivative of both sides, du becomes, what's the derivative of natural log of x? 1 over x. So we're kind of wanting to see this as 1 over x times maybe 3 natural log of x. So separating, oh, that's the derivative of natural log of x. So we want natural log of x to be at dx. We divide both sides by x, 1 over x, or actually, I guess we could think of, we multiply both sides by x, right? X divided by x. So this is dx equals x du. This is a little bit backwards of how we've been doing this so far. The extra part was always in the denominator. This time the extra x is in the numerator so that it can cancel out. You could, but I guess whenever we have a number, we can also always at the very beginning just take it out, and then it's not going to bother us, as long as you remember about it later on. Okay, so I think that's you could put 3 natural log of x, and I think it would be okay. But we could also just put the 3 out here and just say let's just worry about the functions part. And so now let's make our substitutions. So natural log of x is going to become u. So we've got our 3 that I moved outside. Natural log of x becomes u over x. Dx is up here in the numerator. So what we're going to replace it with is this x du. The x's cancel, x divided by x. It's looking nice, isn't it? Just now integral of u du. So again, so we integrate u. U is just u to the first power. Add 1 to the exponent, so we've got u to the second power. Divide by that new exponent, and then don't forget about the 3 that we got sitting out there. It's up in the numerator, plus a constant. And it's, if you forget the plus a constant, again, I'm not even going to, if you can integrate, you'll be fine. But if you remember, that's good too. It should be there. And then now we back substitute. What was u? U was natural log of x. So our final answer is 3 natural log of x squared over 2 plus a constant. Okay, so when you see integration with natural log of x over x, something, go for the natural log of x as our substitution. It's kind of, it was the trickiest. To my way of thinking, it was the trickiest one they had in there. It just took a, and I was asking for your input because I wasn't quite sure where to go, and I was hoping somebody would give me some direction, so thanks. I was going to wait. Okay, is that good? Substitution, be able to, it shouldn't be any harder than any of these. So again, if you work through those, there's videos with each of them worked out. Just make sure it all makes sense. Okay, so let's take a look. These ones are similar. Maybe we should see, what do we have? Riemann sums. Yeah, here's a, use a Riemann sum to estimate the definite integral with n equal 4 subintervals. Shall we take a look at a Riemann sum? Yeah, okay. Now you can use your program, and again, if we want to see your work, you still do a little bit, but remember with the Riemann sums, we don't actually integrate this. We're using this as our function. We're getting the area under that curve. And that's what the Riemann sum program will do for you, and it will show you a graphic of it. You could, do that stuff for, let's see, let's do this. There we go. And oops, make this a little bit. Here we go. It's just delete that. We'll start with a new one. And incidentally, I'll post this video, and then I've also got another class tomorrow morning at 7:30. We're doing the same thing. We might work similar problems. We might work different ones, but I'll post that one as well, so there might be some new things in there. So what are we doing? We are doing a Riemann sums. We're going from 2 to 3. 1 over 1 plus 2x dx. And in intervals, n equals 4. Okay, so bottom line is just a kind of a rough sketch. We're going to go from x equals 2 to x equals 3. There's some kind of function here. We're going to make 4 rectangles from the left side. And we're going to get the area of those 4 rectangles, whatever they are, where the height of the rectangle, so each rectangle will have a height of whatever this is, this delta x. We figure this out first. We want 4 intervals. We're going from 2 to 3. So we take the endpoint minus the second endpoint minus the first endpoint and divide it by 4. 3 minus 2 is 1. divided by 4 is 1/4 or 0.25. So the base of each rectangle will be 0.5. So I'm going to go over here. I'm going to multiply everything by 0.25. And this is sort of the shorthand. You would actually take each rectangle as base times height. So you'd find the height of each times the base. But remember, the shortcut was to take all the heights, add them all together, and then multiply by the base at the end, so you didn't have to do multiple things. So then I want this function value. Let's just call it f of x. I want 4 of them, and I want to start at 2, so because they're left hand, right? This says with the integral, use a left Riemann sum, so I want f of 2, and then I want f of 2.25. Notice I'm just adding the sort of the width of each rectangle, and then I'm going to want f of 2.5, and then I'm going to want f of 2.75, and that's 1, 2, 3, 4 heights, and this will give us the Riemann sum. This is what the Riemann sum is. And again, you could use that Riemann sum program, but also this wasn't too bad. The way I would go about calculating each of these is not by hand. You could plug it in for x and then go 1 plus 2 times 2.5. But what I would do is I would pull up my graphing calculator. Where's my graphing calculator? It's over here. Let's see if it'll be ready for me to use. Always takes a little bit to load up.
How did you notice go by 2.5 from 2 to 3?
Because you go from the interval, the starting of the end interval, we subtract them. That's the whole interval. And since we want to divide that into 4 subintervals, you take that divided by 4, so 1/4. 1 divided by 4 is 2.25.
How come you don't go, you start at 2, how come you don't go all the way to 3?
We do, but the 3 is on the right-hand side of it, right? The 2.75 is the height, and then it goes over till 3.
Okay.
So there's always sort of 1 left. If we went right-handed, we wouldn't use the 2. We would use the 3 instead of the 2. So you always don't, when you're in this calculation, you won't use one of the endpoints. Since we're always doing left-hand, we start with the beginning, but we will never have the endpoint as one of our calculations.
Okay, that can be the same on the test. We're not going to do right.
Yeah. In the homework, we only had you do left-hand. It would not even be any kind of justice to give you a right hand on the test when we haven't had you do any at all in the homework. Oh wow, it came right away. So then I go to y equals, clear this stuff out, we put our function in, just because it's if you go alpha f1, you can get a fraction template with a top and a bottom, and let's see, what are we doing? It is 1 over 1 plus 2x. And again, make sure you have if you don't have something like this, a template, make sure you have your parentheses right. I've seen people put 1 divided by 1 plus 2x, but it's not actually giving you the right values. It's not that fraction. The denominator has to be in parentheses. So if you do this without something like that, you go 1 divided by 1 plus 2x. That's not going to give you right values. Can you see that? Because that denominator just gives you 1 divided by 1, which is 1, then it adds 2x. If you're going to do it this way, insert, you're going to want parentheses. And again, sometimes the biggest problem is getting little things like that, getting it entered correctly into the calculator. So anyway, then we go to, I'll go to table set. Table set is in blue, so second table set. I'd like it to start at 2, and I want it to change by 0.25. That's the So we get those numbers from over here, starting at 2, going by 0.25. And then we go to the table. We've got all our values here. And see, I did it both ways so you can see it works. So 2 is 0.2. 0.2, 0.1818, 0.1818. And I noticed in WebAssign, I was working with someone over the weekend, and they asked like for 5 decimal places of accuracy. And notice this is only giving 4 decimal places. But if you go over, notice you can get as much accuracy as you want, but you have to kind of highlight that. So if it, again, on the test, we're not going to worry too much, but when you're doing the homework, they want 5 decimal places. They want it rounded to 5 decimal places, so you actually need about 6 to get the rounding right. Okay, so this is a way you can get the exact values for however many decimal places you might need. 1 or 0.166. I'll just go to 4 for this, and then 2.75 is 0.1538. Okay, we're going to add all those together. We'll multiply by 0.25. Remember, 0.25 is the base of each of those that we factored out. These are all the heights of those rectangles. We will have the area. Okay. Again, then we go back to our calculator. I'll go second quit to get back to the main screen. We add these together. 0.2 plus 0.1. Oops. 1818 plus 0.1667 plus 0.1538 is equal to that, and then I need to multiply that by 0.25, and that tells us our area under the curve should be 0.1755 or 56, rounded to 4 decimal places. Okay. So some of this, I mean, you could just see, as long as you know you got this, maybe you don't need to write all this out, because that's, you're going to put that in and look up the table, and the table will give you, yeah, go 2.25. Since we need 4, just count the first 4. You got it, add those numbers together, multiply by the width, and you've got the area. Okay, 1 Riemann sum. Just like in here, they have a couple of them for you to practice, be able to do it. Questions? Okay. And let's see if I don't think I have to reload. Oh no, I do have it. So if you're doing, I'll just walk through this one time with the Riemann sum. If you've got this program, you would hit enter, enter again, and then you might have to hit enter one more time if it gives you a messy screen, but it'll ask you to input your function. So let's do that. 1 divided by parentheses 1 plus 2x. Lower bound is 2. Upper bound is 3. So that came right from the problem. Partitions, that's n equals 4. So we just put 4. It shows us the graph, but we're not done yet. It says press enter, so we'll press enter. And then now it asks which kind. So it does many different kinds. We're only sticking with the left sum. So we'll come down to left sum, hit it, enter. It shows it to us, and look at that, 0.17558. And you see it. This is what I like. You understand what you're getting, right? I have a way to check this. If I forgot to multiply by 0.25, oh wait, why didn't, oh okay, I forgot that part. If you use this, use it as a good checker. And it provides that, and you kind of see exactly where it's getting it. These are the left-hand sums, so that was the f of 2, f of 2.25, 2.5, 2.75, or yeah, whatever these are. Okay. Yes.
You still have the transport table?
I do. And if you'd like it, I've got my calculator and I've got it. So if you haven't got it, bring your calculator. I'll even do it the day of the test if you want. But the thing is if you haven't practiced, it might not work well for you, because how do we get out of this thing? We have to go to 7 quit. So sometimes if you forget and you're trying to quit out, it won't crash itself out very nice. So you do 7. Now we're we're not out of the program. If you hit enter again, you're right back into the program because it's in its memory. So I've done this before and I go, oh shoot, I'm back in here. How do I get out? You got to go forward. So you have to put something in here so that you can get to that next menu to get out. And I'm just putting in stuff. Oh, let's see. Maybe it'll let me out this way. Quit. And then I'm going to
Press clear.
thank you. That's the button. You push clear and then it's out of, oh nope, it's still in the memory. So it's just be aware of this so that when you want to get out of it, quit, clear, delete, and then I'll put like 9. So now something else is in its memory, and so I'm safe. Okay, something like that. We good on that part? But again, I like programs like this because you see exactly, it gives deeper understanding what you're doing. What time is it? 3:42. We got about 30 minutes. Applications. I don't remember doing many of those. 13.4. Maybe a few of those. Area between curves, be happy to do any of those. Again, we've got a whole day. You could look through those. The area between curves, I think there's that one we did in class is a nice template of what you'll need to be able to do, so follow that one. Look at that graph. What would you like to see? Or would you like to start working on stuff so you can know what questions you have? I mean, this is all, there's no magic about review. I could show you, whatever I show you is not going to do it. It's you got to get in the driver's seat, right? You have to be driving it. You have to test it with your notes. You have to test it yourself without the notes. Do you remember it enough that if you don't have your notes, because that's how you take the test, right? So the more you can get yourself to that place where you can almost make up a shorter version, and that's what those highlighted questions are, is that there's less stuff there. If you just work the highlighted ones, it'll be closer to just kind of like working the test. And then choose some other ones from the review, a couple from each of them. One thing you don't get is the multiple choice, but the multiple choice, when you come to that, there's the advantage that you're able to just choose the right. You can look at the answers, right? And you can sometimes narrow it down. But you still should be able to get through it. Yes, sir. Number 1? Oh, because it's highlighted. Yeah, sure. Okay, so find the area of the region enclosed by these two curves, x minus x squared plus 6 plus 2. Two x squared plus 9 x plus 4 or minus 4? Minus 4. That's where I was messing up so bad, was my pluses and minuses. Okay, so there's going to be two curves. You can kind of see they're both x squared, so they're U-shaped. One has a negative x squared, so that'll be upside down, and the other one will be right side up. So we could kind of visualize this without even graphing it. One of the things we need to do is we need to find the points of intersection. And we want you to do that algebraically as well as graphically, because the graph will catch it. So the first thing is we're going to look at, they have an intersection where they equal each other. So we want to see that you can take negative x squared plus 6x plus 2 equal to 2x squared plus 9x minus 4. Set the two equations equal, or functions equal to each other. That gives us any points of intersection. Let's add x squared to both sides, because basically with a quadratic, what you're going to be thinking is we're going to try to get it equal to 0, not equal to x, because that typically doesn't work with quadratics. So we add x squared to both sides. That cancels. We get 6x plus 2 equals 3x squared plus 9x minus 4. Again, since we want to get it equal to 0, let's do this in one step. Let's subtract 6x and let's subtract 2. That will make this side 0. What we do to one side, we've got to do to the other. So let's just do it in one step instead of two. This whole side becomes 0. This becomes 3x squared. 9 minus 6, 3. X. Negative, negative. They're still negative. 4 and 2, so that's 6. You could factor out a 3, which will make this a lot easier to work with. So notice some algebra here. We can cheat a little bit. I'm going to show you with the graphing, but at least be able to at least show me that you know how to set these equal to each other. Okay, divide both sides by 3. That's gone. This is still 0. Factor this. X squared. Oops, not x squared. 1 times 2 is 2, so this will be 1, this will be 2. It's negative, so one of these has to be negative, but the middle term ends up being plus 1, so we need a negative here and a positive here. So again, this equals 0. So we get x minus 1 equals 0, x plus 2 equals 0. Add 1 to both sides, we get x equals 1. Over here we get x equals negative 2. So those are our 2 points of intersection. What those are going to become are our boundaries for the integration. So we're going to go from negative 2 to 1. And the other way we do to check this is we clear this, clear that. We put the two functions in and graph them. Going to zoom standard number 6 just to get a nice size window. Should fit there. Fits pretty nicely. I can see maybe I want to go a little bit further down. So I go back to my window, make my Y minimum, maybe make it negative 15. And then I think it'll fit just fine. Yeah, I can see the 2 points, and I can see that's negative 2, and then positive 1 is where they're intersecting. I can also verify second calc, intersect, enter for the first curve. Notice it's asking the question first curve. I hit enter, jumps to this one, says is this a second curve? I say yes, and then I hit enter for a guess. Gives me the closest intersection, x equals 1, so we got that. And then I do it again, second calc, intersect, enter, but for the guess I want to be closer to the other intersection, and it will tell us that that is x equals negative 2. The point is not as important, but we want to get the area between these two curves, and so the way we do that is We're going to integrate, oh wait, first we have to say which one's on top. The blue one's on top. Which one's the blue one? It's the negative x squared. So you take the one on top minus the one on bottom. So we come back here. We'll go ahead and do this. So we're going to integrate from negative 2 to 1, negative x squared plus 6x plus 2 minus.
How do you know which one's on top, like as soon as you got it? Or do you need the calculator?
You need the calculator.
Oh, you have to.
Yeah. I mean, unless you're a genius, and I'm not. Or graphing, unless you can, aside from that, part of it is that negative x squared we know goes down like this, so it's probably going to be the one on top, so that, you know, just in, if you don't get it graph, but graph it is the best way. The negative x squared is going downwards, it's probably going to be the one on top. But the thing is half the time I'm wrong.
Yeah.
You know, so it's, you got to try to visualize the graphs, and I'm not, because I've got this graphing calculator, I just plug it in and it'll do it for me. And so I'm not real good at that, because we don't need to anymore. It's like, just graph it. And especially if you got colors. Colors are easier to see. So then, and then we subtract the second one. And again, what I'm going to do is I'm going to change all the signs on this. So 2x squared was positive. I'm just going to make it negative. 2x squared. 9x was positive, so I'm going to make that negative. And then negative 4 was negative, so I'm going to make that positive. So when you're subtracting something, you just change all the signs. That works best for me. I make fewer errors that way, rather than putting a parentheses and then doing another step to distribute. I just do it while I'm doing it. Okay. So again, part of this is see what works for you. We're going to combine like terms. So this will be similar to what we did throughout this. Negative x squared, negative 2x. We're going to get negative 3x squared, positive 6x, and minus 9x. We're going to get a negative 3x, plus 2 and a plus 4. We get a plus 6. We integrate that from negative 2 to 1. And then, and dx, I guess, you know. And then from here, this is just like a problem from the indefinite integral. We integrate it and we take the boundaries. We could even do it all graphically, right? You could also remember check here. And if you want to in advance have this program, we know y1 is on top. So remember I did this thing with vars. So I came to there and I went over to y vars. And I said I want y1, and I'm going to subtract vars, y vars, enter y2. So I'm going to subtract y1 minus y2. I'm going to turn off the other functions because otherwise I need to leave them there, remember? But if I graph everything, I got too many things going on. So this will graph just the intersection of those two, or those two being subtracted. So that's all that's left. And know it's going from negative 2 to 1. And now I go second calc. I'm going to actually have my calculator do the integration for me. Lower limit was negative 2. The upper limit was 1. And our answer should be 13.5. So now I've got something to shoot for. When I do it by hand, I know what I need to get.
Is there videos on the calculator stuff?
Yes. In classroom, I'm recording this, so that's where you kind of slow it down and maybe watch it frame by frame until you get the buttons, and then do it yourself a few times. All right. Does that help? Okay. And again, what we would do here, we would now integrate this. So the 2, we'd add 1. So that would be, if you're integrating by hand, that's going to be negative 3x to the third divided by 3, right? This is negative x to the first, so it's going to be negative 3x squared divided by 2. And then 6 becomes plus 6x. and then we integrate that from -2 to 1, plug in 1, and then plug in -2 and subtract those two, we should get 13.5. Well, you put the upper end in. We're running out of room, so you put 1 in for x. So I'll just put that as f of 1, and then you subtract f of -2. So you get those two values, and what we should end up with is 13.5. Okay. Anything else? We good? Good. Just have one thing to share with you. I don't know, you probably noticed, but when I look in the mirror, I don't even recognize myself anymore. This weekend, I decided I've been thinking of myself as an old man too much. I'm turning 62, and I was into this. I says, I'm going to color my hair black again. Hasn't been this color since I was in my 40s. I've had white hair for a long time. Shaved off. It says, oh, I look new. So I feel younger. I look in the mirror, I look younger, so my mind is going to say, you're not an old man anymore, you're still young. So feel free to change your look whenever you need to shake it up and get yourself into a bad thing and keep moving forward. We can be whoever we want to be. Be it. All right. So take your time. If you want to hang out and do some work, I'll hang out with you as long as you want. Good luck on your studies. You're welcome to come tomorrow morning at 7:30 if you want. We'll do it again. Hi.
Actually, on your Tuesday and Thursday class, but like I have a request. Can I do my exam on Wednesday?
Of course, yeah.
Thank you.
I had someone from Wednesday who wants to do it Tuesday, so she'll take your spot and you take hers.
Oh, thank you.
Of course, you're welcome. Thank you.
See you.
Okay. Hi.
I don't know. I sent you an email. I don't know if you got it, but I have on on Wednesday